giant insects, tiny mammoths, and whales that used to be small on land. In the story of size, expectation gets turned upside down. Rats are the heroes. Ants are the kings. And people are getting bigger all the time.
People will probably be 7 or maybe even 8 feet tall.
Size matters, right now on Evolve. What if there were a world where the big creatures were small and the small creatures were big? In fact, we're living in it. The sizes of different animals seems fixed, but in the long view of evolutionary time, they are ever-changing and full of surprises. The world's most massive land animal today is the African savanna elephant. The biggest was 13 feet tall at the shoulder and 24,000 pounds. Far smaller, of course, are the tiny ants scampering underfoot, weighing in at 1/1000th of an ounce. The elephants outweigh the ants, right? Wrong.
Biomass is the sum total of the weight of a group of animals or plants. What's amazing is that the biomass of ants makes up 20% of the biomass of all other animals on the land, even though each individual ant is tiny.
In fact, ants outweigh elephants by more than 10 to 1. Elephants, 3 million tons. Ants, 33 million tons. Weight, length, height. Nothing is fixed. Nothing is certain. Size changes because size can determine an animal's fate.
Fundamentally, for animals, size matters. It makes a difference to every interaction you have with other organisms, and it makes a difference to the way you live in your environment. It affects how much you need to feed, it affects what you can feed on, and it affects what's going to feed on you. Everything depends on size.
The story of size is an unending series of outlandish science fiction tales. Bugs as big as birds, elephant relatives as small as ponies. The only difference is these stories are scientific fact.
I would love to have a house mammoth.
Pygmy mammoths, relatives of elephants, evolved on the Channel Islands off of California. Paleontologist Larry Agenbrod was the first to identify these full-grown but tiny mammoths back in 1994.
Got a phone call from Channel Islands National Park, and they explained they had a big skeleton being exposed on the island. Could I determine whether it was a mammoth or something else?
Mammoths emerged about 1.8 million years ago, and some species were alive as recently as 4,000 years ago. Mammoths were larger than modern-day elephants, up to 14 feet at the shoulder. What Agenbrod found on the island that day was strangely smaller. At the Mammoth Site Museum in Hot Springs, South Dakota, Agenbrod compares his beasts.
Here's a femur of another mammoth. It's the same femur as we got there, a right femur, but you can see that it's very small, only a fraction of the size of this big Columbian mammoth.
A study of the wear and tear on the bones determined that the smaller animal was not a juvenile. It was a fully grown adult. Years of digging since that first find have revealed that an entire community of pygmy mammoths evolved on the island.
On the island, I'm finding the average size about 5.5 feet.
These mammoths were 1/10 the weight and half the height of their cousins on the mainland, and lived there as recently as 20,000 years ago. Why did the mammoths evolve to be so small? Agenbrod knew the environment played a role, and that strange things happen to an animal's size on islands. On the Galapagos Islands in the Pacific Ocean, tortoises can balloon to 700 pounds, 3.5 times continental size. Indonesia's Komodo Island is home to the world's largest lizard, the 10-foot Komodo dragon. These giants thrive, cut off from predators. So why would a mammoth shrink? Agenbrod looked to the island history for clues. He discovered that over time, sea levels rose. And what was one large island with a broad coast became 3 smaller islands of steep and craggy peaks. To survive, the huge mammoths would have to find grass to eat higher and higher on the steep slopes of the island's interior. And for that task, being big was a huge disadvantage. Like a poorly designed SUV, their center of gravity was too high.
I put these specimens on slopes and find that the continental mammoth could only handle about 20 to 25 degrees, whereas the pygmy mammoth was comfortable with up to 35-degree slope.
Over many years, the big mammoths died out. The smaller ones survived, mated, and bred generations still smaller, until the pygmy was all that was left.
In evolutionary terms, we're looking at adaptation. So the island selects for a smaller animal capable of getting to upland pastures.
Like all animals on Earth, the size of pygmy mammoths was determined by a complex cocktail of factors. Here on this island, food supply and the lay of the land were enough to shrink them to 1/10 of their original mass. They were able to adapt and survive until humans arrived on the scene.
So I think these little beasts saw the first people arrive on the island, and the first people that arrived on the island saw a meat source that was manageable. I kind of regret the fact that we didn't have an island where nobody ever got to. They were still on Wrangel Island 3,700 years ago. That's when the Egyptians were piling rocks and make pyramids.
Agenbrod holds out hope that even though humans were a major factor in their demise, someday humans might engineer the mammoth's return.
I'm for cloning if we can bring back a mammoth. I see no reason not to bring them back if we have the skill and the technology to do so.
Whatever you have imagined in your wildest dreams now becomes a visual reality.
This ad for an old science fiction flick shows a bee the size of a car.
What's it doing? Sealing us in.
Insects never got that big. But in the science reality of 260 million years ago, the fossil records clearly shows that there really were bugs like Menonura, ancestor of dragonflies, buzzing around with wingspans of 3 feet. Arthropleura, the 7-foot-long crawly ancestors of millipedes. And giant mayflies over a foot long and bigger than a blue jay. It turns out the bugs grew big because of an excess of oxygen in the atmosphere. Now, in a lab in Arizona, paleontologist John Vandenbrooks is working to see if he can grow bugs big again.
We're rearing insects in the lab here under different oxygen levels to see how it affects their modern development.
The most massive bug in the world is the South American Titanus beetle. It can range up to 6.5 inches long. Why can't it grow bigger?
Today's oxygen level is approximately 21%, and contrary to the popular view, oxygen actually varied greatly from that value through geologic time.
Oxygen is at its highest recorded levels when insects are giants. Could this be why they could grow then and not now? This video X-ray shows a beetle breathing, not through a closed system with lungs and a bloodstream carrying oxygen like humans, but through a series of tubes, like an open-air duct system, bringing in air directly from the outside world through the insect's hard and inflexible shell. These straw-like tubes are called trachea, and they are what keeps today's bugs from getting too big.
With increased body size, the amount of that internal body that's taken up with trachea, or the respiratory structures in insects, increases.
As the bugs get larger, the bigger air tubes squeeze out the muscles, and a maximum size is quickly reached, because a bug without leg muscles can't move and gets eaten. Vandenbroek's bugs were fed on oxygen levels amped up from today's 21% of the atmosphere to the same rich 30% oxygen mix that existed in the time of the giant insects. The result? 25 to 30% larger bugs. Because the trachea can draw enough fuel, staying just the size they are. With enough generations, who knows how large these oxygen-fed bugs might grow? What if oxygen levels rose again? Would the ad for that old science fiction movie be a coming attraction for our own future? The answer is, likely not.
With higher oxygen levels, an insect may be able to achieve a much larger body size, but just because it can doesn't mean that they always will. It's these other factors, such as predation and nutritional availability, that will also work in combination with the environmental factors to really establish what body size that a group of insects or an individual insect will actually grow to.
Oxygen supply is just one of dozens of factors that influence how big an animal can get. Some of these factors, like gravity, we've known about for a long time. Some remain mysteries, like how the blue whale grew to become the largest creature that has ever lived.
The jaws of this animal alone could swallow a small compact car.
Now, these two scientists think they might have finally uncovered the answer to the mystery of the blue whale.
See how much the muscles actually... I've never seen anything like this before.
Yeah, this is unprecedented.
Facing the challenges of their changing environments, creatures have shrunk and exploded in size over time like the images in a funhouse mirror. But there is at least one life form that has kept the same size for 3.8 billion years. Bacteria started small and has stayed that way ever since.
And there's a tendency to think that bigger is better, but really being small is a pretty good trick.
For bacteria, it's been a nearly unrivaled story of evolutionary success.
It's been said that if humans disappeared from the Earth, 99.9% of species wouldn't even notice that anything had happened. But if the bacteria disappeared from the Earth, humans would be dead in a matter of hours.
But it seems that getting bigger is a stronger trend. About 1.8 billion years ago, some single-celled creatures either split on their own or joined with others to form the first multicellular organisms. They were the giants of their day, and they started a trend toward larger forms that would continue. Given a favorable set of circumstances, life tends to size up.
One reason that animals might get bigger through evolutionary time, if you have animals within a species competing with one another, and the big ones are always winning and the small ones are always losing, the big ones have more babies and the small ones have fewer babies, and therefore, over time, you would see a progression from smaller animals to bigger animals, which is exactly what we see for a lot of different groups.
The ocean offers improved chances for some animals to grow bigger because the buoyancy of water takes away some of the strain of gravity. And one aquatic life form has trended up over millions of years to a size so unimaginable that even scientists have a hard time understanding how they survive. The blue whale, the largest creature that has ever lived. Whales weren't always big, and in fact, their ancestors didn't even live in the ocean. Whales started out on land.
The ancestors of whales were sort of dog-like creatures that are most closely related to today's hippos, and they moved back into the water probably to feed on fish.
Millions of years of adaptation later, modern whales emerged, now fully aquatic. Their size, about the same as today's dolphins, until they suddenly hit a mysterious growth spurt.
About 5 or 7 million years ago, whales became huge. They became supersized. We don't really know why that happened. It's very much a mystery.
The mystery of why the whales got big is just one of the many that has baffled the scientific community. No one has ever understood how these massive beasts, 90% as heavy as the Statue of Liberty and nearly as tall, could survive on a diet consisting mainly of one of the smallest foods in the ocean.
Some of the larger species of whale tend to specialize on what we call krill, which are small crustaceans that occur all throughout the water column.
Jeremy Goldbogen and Nick Pyenson, biologists working at the University of British Columbia in Vancouver, believe they are on to the whale's secrets. How they feed and how they grew. They start with what they know for sure. Whales gotta eat.
Large body size means that you have enormous resource requirements.
It's just a basic law of physics. You have such a large body mass, you have to eat a lot of food just to sustain that body mass.
The blue whale needs a ton of food a day to survive. It feeds here on the surface, opening wide to envelop as much as 18,000 gallons of water at once. That's about 30 hot tubs worth. The whale then expels the water back to the sea, while keeping the krill in its mouth. It traps the krill with a unique curtain wall of tough plates dangling from the roof of its mouth, called baleen.
Over evolutionary time, they've lost their teeth, and baleen simply hangs down. It's a simple sieve mechanism that will filter out prey from water.
But even with baleen, the whale only captures about 20 pounds of krill at the surface. That means 100 meals a day, a seemingly impossible task.
It makes you wonder whether or not the baleen whales can meet their daily energetic requirements.
Clearly, the whales could not be so big unless they ate enough. Could their size be related to the way they got their food? A huge break in the case came by accident. In 2003, Goldbogen worked on a joint expedition with Scripps Oceanographic and Cascadian Research that attached recording devices to whales with suction cups to track singing behavior.
The tags measure such things as how fast they go, how deep they go, when they're swimming.
But the whales didn't sing and the data seemed useless until Goldbogen realized that the whales were acting strangely, tremendously active. A detailed analysis revealed that the whales were feeding 600 feet down below the surface. Could this secret dining spot hold the key to the whale's success?
This is the first time we've been able to see what a whale is doing underwater, at least a whale this big.
Using the data, the team constructed the first detailed explanation of the whale's deep dive feeding. First, the whale turns head down and powerfully beats its tail a few times to gain momentum. After the first 40 feet of descent, the whale's lungs collapse from increased water pressure, and it drops like a lead weight. Sighting a dense mass of krill, it suddenly opens its mouth, nearly 90 degrees wide. The whale quickly shuts its mouth, squeezes out the water over 30 seconds, and traps the krill behind the baleen filter.
An adult fin whale can execute a lunge in about 6 seconds. It takes 3 seconds to lower the jaws and 3 seconds to close the jaws.
The jaw snap is one half of the technique. The second is the huge cavity that opens up beneath the lower jaw.
So this would be similar to what we have right here under our chin. So their tissue runs from the chin all the way to the belly button.
The research shows that each deep dive averages 4 lunges and lasts about 7 minutes before the whales have to come up for air. In the Southern Ocean alone, krill constitutes 500 million tons of biomass, twice that of humans. And krill appear in oceans all over the world. This plentiful food supply for whales turns out to be a key factor in their evolution as giants of the sea. With dense packs of krill available 600 feet down, even at only 20 pounds a bite, the whales can get enough food in just 4 hours a day, leaving plenty of time for singing. The team thinks that the development of baleen and lunge feeding just might finally account for the whale's mysterious and rapid evolution to supersize 5 to 7 million years ago. One reason that whales can grow so large is that the buoyancy of water helps counteract the effects of gravity. But sauropods, the largest creatures ever to live on land, had no such advantages, yet they managed to grow nearly as big. How did they do it?
Sauropods had necks that were completely out of bounds of human experience.
In the world of big, nothing on land has ever topped the sauropods. A plant-eating subgroup of dinosaurs, sauropods roamed the entire globe 200 million years ago, ranging up to 130 feet long, nearly the length of the White House. They set all the records for land animal size. They were even too big for T-Rex to attack.
We don't find very much evidence of big sauropods being attacked by big predatory dinosaurs, things like Tyrannosaurus rex. Be up to 30 or 40 feet long and maybe 7 tons. These are fearsome animals, but they're just no match for a full-grown sauropod.
These beasts were so much bigger than anything else that has ever lived on land that scientists knew the combination of factors that produced them must be unique. What was the secret of the sauropod's success?
This is Brachiosaurus. This animal is 75 feet long, 45 feet tall, and weighed about 30 tons.
Evolutionary biologist Matt Wadel has been working at the riddle for years. All the conditions had to be just right to produce this freak of nature. He picked up his first clue when scientists discovered that the Earth in the age of dinosaurs was very different from our own.
Sauropods almost lived on a different planet, not separated from us in space, but in time.
What made the planet different was the atmosphere. Recent analysis of fossil records suggests that carbon dioxide levels during the Triassic period, just at the start of the age of dinosaurs, soared to the highest levels ever. As a result, plant growth exploded.
When we grow plants today, under those conditions, they grow to almost double the size.
More carbon dioxide-breathing plants meant more food for plant eaters. And there have never been vegetarians who ate more than the sauropods.
For the very largest sauropods, the daily requirement for food was probably on the order of a ton of vegetation every day. Their heads are just biting machines. Not only did they not chew their food, they couldn't chew their food because their teeth didn't meet up the way ours do. They could just shovel it in and keep getting bigger.
It took relatively little energy for the sauropods to eat. One reason why plant eaters have the potential to get bigger than meat eaters. But as they evolved through millions of years, their growing enormity meant they needed gigantic muscles to move heavier and heavier bones, including the seemingly impossible sauropod neck.
Some of these necks were 40 or maybe even 50 feet long. Now, how does an animal hold up and support and move around a neck that's so long?
Today, the largest neck, at 7.5 feet, belongs, of course, to the giraffe. But giraffe bones are heavy and restrict movement. And sauropod bones dwarf them.
All right, that looks great. This is a neck vertebra of Supersaurus. This is the largest vertebra that we have ever found on Earth. It's 4.5 feet long. Now let's see how that compares to a vertebra from the neck of giraffe. This is one of 7 vertebrae from the neck of a giraffe. This is one of 15 from the neck of Supersaurus.
If sauropod neck bones were as dense as a giraffe's, the 15 vertebrae strand of Supersaurus would weigh more than 10,000 pounds. How could the Supersaurus lift bones so massive with neck muscles so relatively slender? Because the bones have turned to fossilized rock, their weight in life is unknown. But Wadle learned that a graduate student at Brigham Young University in Utah, Brooks Britt, had been using scanning technology on dinosaur bones.
From Diplodocus.
Britt suggested that Wadle scan neck bones to see if subtle differences in the fossilized rock could reveal the bone's original structure.
Nobody's probably scanned a Diplodocus vertebra that's in this good a shape.
The CAT scan will allow the first look ever at the interior of this 145-million-year-old Diplodocus neck bone. The different densities of rock within the bone are invisible to the naked eye, but the scanner clearly reveals that the bones in life were feather light.
There's cavities all through this.
Like car tires, the bones are pneumatic. They are 60 to 70% filled with air. Wadle suspects that the bones were not only light and easy to lift, they also helped get oxygen directly to the muscles, fed by a system of air sacs throughout the neck, similar to birds today.
Sauropods were probably about 10% lighter than they would have been otherwise. Now, those effects ripple through the entire biology of the animal. You don't need as much oxygen. You can grow faster because you don't have to put on as much mass.
Just because they're hollow doesn't mean the neck bones aren't strong. Air-filled cavity design is widespread in engineering, from sneakers to the strong neck-like framework of a construction crane arm.
The material that's get replaced is not serving any structural purpose. Bighorn sheep are butting heads at very high velocities, very huge forces involved. Their horns are pneumatic, so pneumatic doesn't mean weak.
The sauropods had hit on just the right mix to become a freak of nature. Hollow bones, plenty of food, and a huge size to deter predators. They had everything going for them.
You've got dinosaurs all over the place. You have big ones, you have small ones, some of them eat meat, some of them eat plants, and everything's going just fine because they are well adapted to their environments. But then all of a sudden the rules change.
65 million years ago, striking with the energy of 100 million tons of TNT, an asteroid brought the reign of the dinosaurs to a sudden, shocking end. The heat pulse from the blast circled the globe and raised the temperature to 1,300 degrees Fahrenheit, killing the biggest dinosaurs and more within hours. The world was an oven, set on broil. The abundant vegetation was gone.
All of the big animals on Earth were at a huge disadvantage because they were big. Because they needed so much food and there was so little food around, they couldn't survive. Mammals, on the other hand, found themselves at a huge advantage because they were so small.
Every species over 20 pounds, 70% of all life on Earth, went extinct. The conditions for life on Earth were radically reset. Suddenly, tiny warm-blooded mammals, the ancestors of rodents, found their ticket to success. Today, rodents are found on every continent but Antarctica, in over 2,000 species with billions of individuals. And their descendants, every mammal on Earth, including us, would fill up every size niche in the world. In a mass extinction over 65 million years ago, every species that averaged larger than 20 pounds was wiped off the face of the Earth. 70% of all life on the planet was destroyed. But tiny mammals, much smaller than today's rodents, survived.
This guy would have been a giant compared to the mammals at that time.
Evolutionary biologist Felicia Smith works with a creature approximately 1/200,000th the size of a sauropod, but no less important in the strange story of size. The amazing, size-changing wood rat.
Well, wood rats are probably one of the mammals that are most sensitive to temperature.
Bushy-tail wood rats are small where the climate is hot, and 3 times the size where the climate is cold.
Okay, let's go ahead and where? The animals here in the southern part of the range in the Sangre de Cristo Mountains of New Mexico are the smallest. If you go up to the northern part of the range in Canada, 204, you'll find animals that are about 3 times the size.
Wood rats even live in one of the hottest spots on Earth, Death Valley, offering a hint of how those earliest mammals survived when most everything else died in the wake of the asteroid hit.
In Death Valley, for roughly 3 months, it's above lethal every single day. So how are the animals able to get around the fact? Well, for one thing, they're nocturnal, but that doesn't help much when nighttime temperatures are still 118. It's still above lethal.
Smith made repeated ventures into the blistering heat of Death Valley and uncovered the wood rat's survival secret.
The animals build these enormous dens, and we found to our surprise, by burrowing deep enough in the ground, some of these animals were able to get to a place within their den where the temperatures were 36 degrees Fahrenheit, cooler than the outside temperatures, which is an enormous amount. It gives them an edge where they can actually survive.
For the wood rats in Death Valley and those first mammals, being small was an advantage. They were able to hide out and survive on little until food sources returned and life on Earth could spread again. Mammals radiated out into thousands of species, from leopards to rabbits to people. And 3/4 of those species have grown larger over time.
A lot of groups, when you look at the sequence of fossils over time, you see that within a species, animals are getting progressively bigger. It's not true for all groups, but it's true for quite a few of them.
For example, horses in North America have a beautiful fossil record documenting ever-increasing body size over tens of millions of years.
In an evolutionary sense, there's always selection for larger size. You're better at getting mates, you're better at fighting with other individuals. If you're a carnivore, you're better at stealing carcasses from other species. There are lots of reasons to get big.
Blair von Valkenburg teaches ecology and evolutionary biology at UCLA. an expert on wolves, past and present, Valkenburg argues that with size comes risk. As meat-eating mammals grow larger, they reach a tipping point.
It's really interesting. Mammalian carnivores fall into two groups, basically divided by body size. Everything that's less than 44 pounds and pretty much everything that is above 44 pounds.
Above 44 pounds, a meat-eating mammal has to change its diet to eat much bigger prey. Otherwise, it has to hunt too frequently.
Imagine a day in the life of a wolf. And the wolf says, I'm going to eat mice today. So he goes out, he hunts, catches a mouse. Yum, that's good. But I'm still hungry. So let's get another mouse. Still hungry. Another mouse, and another mouse, and another mouse. Every mouse he catches, he's expending that energy that he gained catching that next mouse. So he can hunt all day and never get full, never be satiated.
The balance between size, food, and the energy required to get it means that no land mammal carnivore could ever be bigger than 2,400 pounds, about 700 pounds heavier than the heaviest polar bear.
Animals can't get infinitely big. There are all kinds of factors that come into play. Animals have to be able to get enough oxygen to their tissues to keep their tissues alive. If you're really big, that's not very easy to do. Animals have to be able to find enough food to feed themselves. If you're infinitely big, there's just not enough food in the environment. Also, most animals have to move around on the ground and support their body weight. And if you're too big, that just can't be done.
The dire wolf evolved about 9 million years ago and grew to 150 pounds, twice the size of today's gray wolf, which made it an evolutionary success for a time. But the dire wolf could not adapt when the change in climate killed off some of its prey. After 100,000 years of coexistence with its gray wolf cousin, the big-eater dire wolf went extinct 10,000 years ago. Meat-eating dinosaurs, of course, got much bigger. But even an energy-efficient reptile like T-Rex bumped up against its maximum size.
Tyrannosaurus rex was probably limited in how big it could get because it relied on meat. And there are studies that suggest that Tyrannosaurus rex was as big as a carnivore can get. Sometimes you can't just keep on getting bigger.
What about human beings? Are we evolving bigger and taller all the time? And are we therefore at risk for extinction?
There's no question that over the last 100 years, people have been getting taller, especially in North America. If you go to an old colonial home, the doors are shorter, you feel like a giant walking around in there. But is that a result of evolutionary change, or is that just a result of differences in nutrition? That's something we don't exactly know.
Human height is something of a mystery, and the story is full of surprises, starting with the fact that we are now shorter than we were 50,000 years ago.
Believe it or not, agriculture was not progress.
Across the globe, human height has risen in the developed world over the last 150 years, from an average of 5'3" for men to 5'8", with women about 5 inches shorter. What accounts for this growth spurt? Better nutrition? Or an evolutionary trend brought about by mate-choosing behavior that Charles Darwin named sexual selection? Or to put it in the terms of the mating ground, chicks dig tall guys.
In general, I prefer taller men.
If he has a larger and stronger physical appearance, it just looks better.
I like them to be bigger than me to feel more protected.
It's just more attractive.
Just something kicks in.
Mate preference is one of those things where people don't always have all that much insight into their own preferences.
Evolutionary psychologist Robert Kurzban studies human mate preference, gathering data in the controlled conditions created by a hurry date.
You just have 3 minutes. And of course, this makes it an interaction where first impressions make a big difference because there aren't second impressions.
What counts? Sparkling conversation?
As far as we can tell, the conversation doesn't matter at all. It doesn't matter what they're saying. It doesn't matter. What they're choosing on are these physical features, how skinny you are, how tall you are.
In choices influenced by deep evolutionary drives millions of years old, men desire women with low body mass index, the thin ones, and women desire men with size.
Just like in the non-human animal world, when people are looking for a short-term mate, people look for those things that correlate with good DNA. What we found was that the taller a man was, the more likely he was to get selected by women.
A recent study of a West Point graduating class showed that the taller the man, the more children he has, mostly because of marrying a second time later in life. All across the globe, the story seems to be the same.
Everywhere in the world where there are people who arrange marriages, one of the criteria that's always given is that the husband should be taller than the wife. Taller individuals might be sexier in that sense.
Biological anthropologist Barry Bogan has been unraveling the mystery of human growth at the University of Loughborough in England for over 20 years, starting with the earliest known human ancestors.
What I have in my hand here is a cast of the femur or thigh bone of Lucy, the famous Australopithecus afarensis. Lucy and her kind were quite short, shorter than modern-day pygmies, under even 4 foot 8 inches tall for the men. You can see that this femur would fit in just about here.
From that humble beginning, humans grew until they reached an average of 6 feet tall, 50,000 years ago. It turned out to be a high point that we have yet to touch again.
Things change, and we see a decline in stature, down to 5'3" adult males.
What could cause this reversal of fortune? As elsewhere in the story of size, a changing environment. It killed off the prey humans fed on and forced them to find new sources of food.
People were not eating as well. People who previously hunted and gathered their food just couldn't find enough. And they started to harvest foods that probably were growing in their garbage piles. The seeds sprouted up and they said, hey, we can eat some of our garbage.
It was the start of agriculture, and for a long time, it was a disaster.
Believe it or not, agriculture was not progress. Agriculture narrowed the variety of foods people ate. That resulted in nutritional deficiencies and smaller people.
Good nutrition would be scarce, and height would remain compressed until the late 19th century, when better foods, improved sanitary conditions, and healthcare took the brakes off human height. We caught up fast, and now the developed world averages 5'9" for men, 5'4" for women. Not a record, but a best in the modern era. And the trend is definitely up. Everything seems to be in place for humans to continue to grow. Nutrition, sexual selection, and the general tendency of mammals to size up over time. So, are we headed for the land of the giants?
If we were to come back in 200 or 300 years, the human species would probably be 7 or maybe even 8 feet tall. It seems hard to believe, but the fact is, humans have been getting taller every generation. It's a combination of nutrition and genes, but that combination is making our entire species bigger than they were.
But not everyone agrees.
Will we be 7-footers and 8-footers and taller? I don't think so. There is a cap on healthy human height.
Bogan points out that above 7 feet, people today encounter increased medical problems associated with their height. He believes that the greatest average height we can most likely achieve is a healthy 6'2" for men and 5'8" for women.
If I live another 100 years, you can come back and ask me if I was right or wrong.
As human beings and all life on Earth moves to the future, all the factors affecting body size, from mating to predation to environment, will continue to be in play and are likely to produce amazing and unexpected results as size continues to evolve.